All right, we're going to do just one more. This one's a little trickier or maybe a little easier, just depending on how comfortable you are with Lewis structures. This one gives us the Lewis structures for the tricky ones, which is nice, although be aware that you should be able to come up with some of these Lewis structures on your own. We'll practice a little bit in class, but what will really help, believe it or not, is your nomenclature, especially when we start drawing out some of these organic ones where there's carbon chains, and you know, is it single bond, double bond, etc. So practice. If you struggle with those Lewis structures still, we're going to use the same formula as we did in the last equation. We want to know how much energy is going to be input to break all of these reactant bonds. Compare that to the amount of energy released when we reform all of these product bonds. And so I'm going to first just sum together all of the bond energies that are going to tell me the energy required to break all those bonds. I'm going to have 614 kilojoules required to break that carbon-carbon double bond. I'm going to add that to 4 times 413 kilojoules, which is the energy required to break those 4 carbon-hydrogen single bonds. And I will add to that the energy required to break the 1 fluorine-fluorine single bond, which is 154 kilojoules. Okay, so sum all these together, we end up with 2,420 kilojoules of energy required to break all of those bonds that make up our reactant molecules. However, there's energy that's going to be released as we reform these new bonds. In fact, we could represent that by taking 347 kilojoules, which is the energy that's released upon the formation of that carbon-carbon single bond, plus 4 times 413 kilojoules, which is the energy released upon the formation of those 4 carbon-hydrogen single bonds, plus 2 times X. X being the 2 bonds that are my carbon-fluorine single bonds, which I don't know what the answer is. I don't know what that bond energy is because tragically it's been left out of my bond energies chart. However, lucky enough for me, there is an enthalpy change already provided for this reaction, which is negative 549 kilojoules. And as we think about solving the actual question, though, it's just some basic algebra skills to solve for X. It's going to be minus, we can combine these things here and end up with 1,999 kilojoules plus 2X equals negative 549 kilojoules. And then we'll distribute this negative, so we're going to end up with something like, over here we're going to get 421 kilojoules minus 2X, again after we distribute that negative, equals negative 549 kilojoules. Then go negative 2X equals negative 970 kilojoules. Divide each side by 2X, we end up with X equals 485 kilojoules, which is the bond energy for a single mole of carbon-fluorine single bonds.